The gentleman I'm going to introduce next is not only a speaker, but we consider him as a brother and a member, long-time member of Nairobi. So Aaron was the first speaker to travel here at our first conference when we were not sure if anyone will show up for our first conference. He was the guy who actually showed us step to step how to set up the CFP page on Iroku app. Yeah, so he has always been there even when he is not here physically, by giving us moral support and encouraging us to keep pushing. And this year actually is the second time, first speaker to come here twice. So can you give it up for Aaron? Now, thank you so much. Now, Aaron is building a more user-friendly layer on top of blockchain projects. He's an Elixir programmer and crypto mining farm manager. He loves nyamachoma and wants to eat it right now. And that makes us to make an arrangement for that. So give it up for Aaron once more. The gentleman I'm going to introduce next is not only a speaker, but we consider him as a brother and a member, long-time member of Nairobi. So Aaron was the first speaker to travel here at our first conference when we were not sure if anyone will show up for our first conference. He was the guy who actually showed us step to step how to set up the CFP page on Iroku app. Yeah, so he has always been there even when he is not here physically, by giving us moral support and encouraging us to keep pushing. And this year actually is the second time, first speaker to come here twice. So can you give it up for Aaron? Now, thank you so much. Now, Aaron is building a more user-friendly layer on top of blockchain projects. He's an Elixir programmer and crypto mining farm manager. He loves nyamachoma and wants to eat it right now. And that makes us to make an arrangement for that. So give it up for Aaron once more. He's going to present about boom, zap, PoW.
So thanks, that's true. It's great to be here again. I had a really great time last time. I wanted to come in between, but I just couldn't, and now I'm here again. I'd like to come again, hopefully, but thanks again. First of all, so there's a couple of things. One thing is that I just watched a talk that I gave recently, and I said maybe 1,000 times. So maybe people can, in the front row, can do something bad when I say for at least the beginning of the talk. So I'm looking at you two, right? That's good. I like the thumb thing. The other thing is that this stuff is really hard for me to explain. Because it's hard for me to decide which background information needs to come first, and I keep moving things around in the talk, so it's possible that it might still be slightly confusing. See, now I'm going to be hypersensitive about ums, and so will everybody else. It was a stupid thing to do. I will never start a talk like that again. So I am a miner, I guess. I mine at my office where I have free electricity. This is my mining rig. This is one video card here, and the fan is broken. So right here is an external fan that is sandwiched in between the next video card, which also has a broken fan. So there is another fan underneath it. So I have 2 cards. I mine different things. It's free. And yeah. And it turns out when you're a miner that lots of people don't like you very much. You have, first of all, I've been playing video games since the 80s. And Mario, Street Fighter 2, I actually had bite marks in my SNES controller from playing Street Fighter. And gamers hate miners, and they have a pretty good reason. This is a pile of, it's the same, I think it's the same. No, it's not. It's of 1080s. Here's another thing where the prices, we kind of make it so the prices of graphics card go up and up. People think that we're hoarding cards. But then there's this, so I don't really care very much. Another group of people that hate us is environmentalists. And this is actually a picture of me from when I was whatever age that is. I think I'm maybe like 5 or 6. And I've been an environmentalist at heart for my whole life, hugging trees at a young age. And they're completely right. There's the energy of Ecuador, I think, goes into mining Bitcoin, and that's pretty insane. There's a good reason for it, but I mean, it's way too much energy. So this is me. I am on Twitter. Maybe follow me, maybe not. I'm in a complaining phase right now. So if you don't like complaining, don't follow me on Twitter. I do mostly Elixir right now. I throw some Ruby in there. Just all of the things that PJ was saying people were jumping to. I jump to things. And I love Elixir. If you want to talk about Elixir at some point, come talk to me. I manage a small-ish mining farm. It's in a container in Austria. And yeah, that's a thing. And I've been doing more blockchain-related projects. I'm thinking of getting a job at some sort of a interesting blockchain project. One of the ones that I'll talk about for a second at the end if I get there. So I'm going to use Bitcoin as a basis for all of this because it's started everything, and it's a lot of the projects that you're seeing these days are just, they took Bitcoin's ideas and changed them a bit, or improved certain parts, or added some things. So we're just going to straight up talk about Bitcoin for all of my examples. And Bitcoin's main goal was to create a way for people to exchange value in a decentralized way, so not relying on some sort of a third party. The way that a lot of these things are working now, you'll have banks, you'll have, for example, M-Pesa has a company that controls all of the things that go back and forth. So you pay, and then there's a central authority that says, okay, is this transaction okay or not? Yes, it is. Cool. Then we will go further with it. So there's always this kind of a bank or some sort of a middle person or a middle corporation that decides whether each transaction that goes in and out is valid or not. And Bitcoin, the reason that they wanted to be decentralized was because of a few things. And one thing specifically is, this is, I think, January 3rd, 2009, the Times. You have this actually over here, I guess, sorry, people over there. This here was in the Genesis block, so the original block for the whole Bitcoin blockchain. This is hex that was dumped, and you can see that there is this headline in the newspaper was inside the Genesis block. So it's a political statement saying, hey, banks keep getting bailed out. We are paying taxes. They're gambling with our money, and we want a way that we actually have control over our money instead of the banks. So there's a few problems that you have to solve with this sending money back and forth in a decentralized way. The ones that I will go into a little bit are something called a Sybil attack, and Sybil comes from the name, I think it was a movie. It was about a woman with multiple personality disorder. I think it's called something else now. And it has to do with kind of creating a lot of fake personalities or entities that it's cheap to do that, and then it seems like they're real, but they're not. They're controlled by one group. And double spend, which is kind of the main thing that stopped digital currencies. There were digital currencies in the 90s already that were created, but one of the main problems that they couldn't solve in a good way was the double spend problem. So I'll go into a little bit of background about kind of what these things are, these terms, what's going on, and what Bitcoin is, what a blockchain is a distributed immutable ledger. So I will describe kind of what those different things mean. A ledger is a record of transactions going in and out. So I pay you something, it shows that that money leaves my account and arrives in your account, and it's a copy of all of those things. Since in the case of Bitcoin, since the beginning of Bitcoin's creation, since 2009. Distributed, there's no central authority like in the case of banks. Each Bitcoin node has a complete record of every transaction that's ever happened. Immutable means that you can't go back in time and change things that happened and then make them different. So there's a way to show that if something small gets changed from 3 years ago, that it changes everything that happens after it. So, for example, we have our blocks coming in. Each block has a reference to the block before it. So here's our next block. We keep getting blocks. Blocks keep coming. They keep referencing ones further back. If we change one of the blocks, change one of the transactions, change the ins and outs, any of those things, then this reference back changes because the kind of the signature of the block changes. So everything that happened after it has also changed. So you have this kind of proof that from back in time, these things have not ever changed. So a block itself is it contains a list of transactions. So transactions refer to a previous transaction as the in, so the money that the coins that you're dealing with that you want to spend. And then there are outs, which there's an address on them of someone's Bitcoin address, someone's Bitcoin wallet, and then there is, then there's the amount that you're sending. Oh, and one more thing, there is also some metadata in the header of the block, or the header of the block is some metadata that we'll talk about later. It's one of the things that makes proof of work possible. And then there's a couple different kinds of nodes. So one node is called a full node. So you just boot up maybe a virtual server somewhere, and this full node contains the complete history of Bitcoin. And so all of the transactions, all of the blocks, everything that has happened. So I think at this point it's around 120 gigabytes in size you need to run this. And it serves a couple of purposes. So it has a port open on it, and it will communicate with other nodes and accept requests from other nodes. So it will receive, I want to send currency to someone else. My wallet will sign that request, sign that transaction, and then send it out to nodes that it knows about. And then those nodes will tell all the rest of the world about its transactions. It also, when miners mine a block, so a block is mined, we want to take that block and send it to the rest of the network. The miner will send it to the nodes that it knows about, and then they will also send it out to everyone they do for eternity. And a miner is a special node. It sometimes can contain the whole history, but usually doesn't. And the miners are the ones out there doing the proof of work and verifying transactions and blocks, and yeah. So this is Bitcoin D running on a server. Bitcoin D is the actual like binary that you run on your server. And this is like our nodes. These are all virtual machines somewhere all over the world. So one receives a transaction. It sends the transactions to the nodes that it knows about. They send transactions to the nodes that they know about. And then eventually, the whole world receives, all of the nodes in the entire Bitcoin network will receive these transactions that they put into a transaction pool. So we'll look now at kind of what is a Sybil attack. We have our bad actor, sometimes referred to as Mallory. Mallory has a Bitcoin, or many Bitcoins. And we have just Dude, and Dude has a Lambo. There's a lot of references to Lambo in all of the cryptocurrency communities. It's pretty obnoxious. So I'm actually bringing that further. I'm being more obnoxious because I already know that it's obnoxious. We have some nodes. We have some other nodes. Great. So we want Mallory to send Dude 40 Bitcoin. So we create a transaction, and this is 40 Bitcoin for the Lambo, of course. We create a transaction, and we send the transaction to, like, let's say half the nodes. Then Mallory is like, this is what I'm going to do. I'm also going to create a 40 Bitcoin transaction and send it to myself or to another wallet that I own, using the same transaction input that I did for the transaction to Dude. So I'm going to send this transaction to all of these nodes over here. So all that I have to do is make Dude think long enough that I've actually spent the first transaction, when eventually probably what happens, what we can guess on, is that the network will catch up and actually believe the second one. So since both transactions came from the same transaction input, if more of the nodes believe that the second transaction happens, then the first one just becomes, it goes away. It just disappears. Everyone says it's invalid, and it disappears into the ether. So Mallory ends up with the Bitcoin and the Lambo, and Dude ends up with absolutely nothing. So proof of work. This is gonna. That's nice. Nice effect. So how does proof of work? So in Satoshi's original white paper, he used spam protection as an example. There were, what's it called, hash cache, I think, is spam protection where each time you send an email through this network, you're forced to do some sort of a calculation. So maybe, I don't know if it used the same thing that Bitcoin does, but let's say you have to guess some sort of a number, and it has to be right. And say it takes a certain amount of time to guess a certain number. So each time, if I'm a bad actor, if I'm sending out a bunch of spam, I have to put energy and time into guessing this number with each of my spam emails. But if I'm a good guy and I'm sending out transactions, or I'm sending out emails to people, maybe I'm sending out 5 emails, that amount of work does not affect me in any way. So Satoshi, whoever Satoshi is, was like, hey, this sounds like a good idea. Maybe we can do this to validate that people are actually putting resources into trying to do things. So proof of work is something that takes a lot of resources to generate or to figure out, to solve, but it's very, very quick to validate. So the way that it works with Bitcoin is that you you have to solve a cryptographic puzzle, and it takes a certain amount of time with a certain amount of hash power. Hash power equals an amount of energy, because you can only do a certain amount of different equipment can do different hash speeds for different amounts of watts, essentially. And so I can say, hey, I see this. They're saying it's valid, and they spent, I don't know, $40 to prove that it's valid. So I'm going to say that this is likely to be the truth. And the way that it works with the miners is that they follow a trail that you have a chain of blocks, and they want to follow the chain that has the most work done, because they believe that the most effort has been put into figuring out to validate the transactions. And the blockchains are constantly forking. So if two miners find a block at the same time, or even slightly different times, and they propagate those blocks out to the network at the same time, you're going to have two versions of the blockchain. So that's what, for example, one of these, this split is. So in this case, the two miners found a block at the same time. So since with Bitcoin, they also make it so a block should on average come out every 10 minutes. So maybe this took exactly 10 minutes. Both of the miners found blocks. And then maybe in less than 10 minutes or 10 minutes later, a miner had found a block, but they used this block as their last reference. So everyone's going to say, I'm not going to follow this anymore because it's safer to follow this one, and I don't want to waste time and energy. What am I doing? Should I do it over here too? Can you all see when I'm doing it over there with it's fine? It's good? Okay. So I'm going to rely on this one then from now on. Thank you. Yeah, so they're going to say, hey, we're going to follow this one. Then there's some cases where two miners find a block at the same time, and then maybe exactly the same time miners find the next block. And so they're like, oh, we were following this one and we got a second one at the same time. Great, cool. But then generally there's a very, 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 very small chance that there will be three blocks found where 3 blocks found in a row where they were all found at the same time, or they were all propagated at the same time. So when this block or this block is found coming off of this chain, all of the miners are going to say, oops, we don't trust this fork anymore, we're going with this fork. So they automatically switch to building off of this block instead of building off of this block. And it's very, very expensive to pick the wrong chain, because then you're putting all of your hashing power, maybe hundreds of dollars an hour, thousands of dollars an hour, into something that's going to disappear. These blocks that are purple, they just aren't anything. No one cares about them. They've disappeared. They don't exist anymore. So if I continue building off of this, when this one was the real winner, then all of my work, all of my money that I put into it, all my resources just disappear. And another thing that's happening in here is these nodes, when they get transactions, when they're creating blocks, if there are double spend transactions that are coming in, if I had already spent the money in a block before, in a transaction before, the new block, then blocks that are built on top of that will not accept a double spend. So I couldn't do, for example, what Mallory did before. And every 10 minutes, on average, there's a new block found, and this is done with changing the difficulty, which we'll see later. And this ensures kind of that these forks happen less often. If you had like a 1-second block time, for example, there would be a lot more chances of the whole network not receiving blocks, so you'd have a lot of forks happening constantly and a lot of people wasting energy. That's why Satoshi picked this this 10-minute block time because it's kind of a balance between speed and the not having wasted energy on blocks that don't go any further. And there's no trust in the system. It's just everyone is agreeing on the longest chain, and that chain has to have the blocks in that chain have to have valid transactions. And it's also based on game theory things and self-interest, where I'm not going to try and do bad things because it's going to cost me lots of money to do bad things, and in the end, it might just make more sense to mine instead of trying to game the system. So we'll look now at kind of a double spend via a 51% attack. So this is another concept that you might hear quite often, the 51% attack. We have our blocks being created, they're going. So at this point, I create a transaction for 40 Bitcoin for a Lambo, and this transaction goes into this block. So the blockchain keeps going on, blocks being built on top, blocks being built, more blocks. So what has happened at the same time is Mallory has created a 40 Bitcoin transaction to himself on a different blockchain. And since Mallory has more than 51% of the block power, or of the hash rate, Mallory can create blocks faster than the main chain on average. So Mallory has their own system over here where they're generating all of these blocks, and they have generated blocks a longer blockchain fork than the original one. So they have, again, gotten their Lambo and created another transaction where they get their money back. So they also then at this point spin up a bunch of nodes and show their fork to the world. And then here's Mallory's fork. Mallory has more blocks in the chain. All of the miners switch, but Mallory already has their Lambo. I probably could have described that better. So if Mallory has less than 51% of the hash power, so which is much more likely. So with Bitcoin, for example, it's in the, I think, millions of dollars or something to be able to have more than 51% of the hashing power. So this would be a more realistic situation. Created my double spend. There's the actual blockchain on the top that's having blocks added to it. The blockchain, the main chain the main fork is ahead. Oh, I'm catching up. Nope, it's more ahead. It's more ahead. I'm catching up. No. Oh, yay. So it's very, 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 very hard once you get behind to catch up ever. So it just would be impossible to eventually catch up. So there have been recently with some altcoins 51% attacks that worked. Verge, which is a crap project, they just, I think twice they got hacked via a 51% attack using the same attack vector, so they didn't fix it or anything. They're just like, hey, cool. And then Bitcoin Gold recently, I think a month and a half ago, had a 51% attack, and then someone else, I feel. So it's something that's out there. It's really happening. And with some of these altcoins, it's easier because it's cheaper to be able to do this, like in the thousands of euros or thousands of dollars a day instead of the millions. And what they do is instead of having a Lambo, there is an exchange. So you have a crypto exchange, and I am doing a 51% attack. I've never described this before, so it might go very poorly. I have a 51% attack. I'm ahead. On my side, I make a transaction to a crypto exchange where I am sending them Bitcoin Gold, for example. So I send them Bitcoin Gold. They wait until there's a certain amount of blocks built on top of that transaction. and then they say, okay, Bitcoin Gold's here, perfect, you have access to it. And then what I would do is exchange my Bitcoin Gold for something like Monero, and then I would send Monero to my wallet, send it somewhere else, and then I would release my mine chain to the world, and then they would see actually that transaction that I sent them of all the Bitcoin Gold, millions of dollars worth of Bitcoin Gold, isn't in the actual blockchain, and they lost all their money. So all the 51% attacks that have happened recently have been from at exchanges, targeting exchanges. So let's look at a block. A block, again, is a block header and a list of transactions. Transaction? So this is, if you look at a block explorer, this is what a transaction looks like. This is, I think, is this the Coinbase? No, that is. So you have this, a transaction coming in, so you're referencing a previous transaction. And then you have addresses, so this is the previous transaction, this is the input. And then you have the output, which is two addresses. One is generally some sort of a change address, and then the other one is to the person, to the wallet you're sending coins to. What's happening here? So if there's any difference between the inputs and the outputs, say the input transaction was for 10 Bitcoin, and I'm sending 9 Bitcoin out the other side, that 1 Bitcoin left over goes to the miner as a transaction fee. This is the Coinbase transaction. So the first transaction in any block is called the Coinbase transaction. This is where Bitcoin or Ethereum or whatever is created. When you create the block, you put the Coinbase transaction in to your address. So when this block gets mined, this Bitcoin would go to the miner's address. So this is your reward for mining, and this is how Bitcoin actually gets created, is in these Coinbase addresses or Coinbase transactions. And there's a validation that goes through with all the nodes, whether if I said this is 9 million Bitcoin, that none of the nodes would accept it as being valid. So the block header contains a few things. This is important for proof of work. We have a version number. We have the hash of the previous block, which I mentioned earlier. This is how we can keep looking back in time and keeping it immutable. We have a Merkle root. We'll look at that in a second. We have a timestamp. Bits, which is the target. This is what we're trying to, when we're solving the cryptographic problem, this comes in, it's important. And the nonce is actually the number that we use that solves the cryptographic problem. So a Merkle tree is a tree structure of hashes of hashes. So you take a thing. Do I have a better thing? No. So you take a thing at the bottom, a transaction, for example, and you do, in the case of Bitcoin, 2 SHA-256 hashes on it. So it becomes just a string of numbers. And then up the tree, so you have 2 transactions, you hash them, and then they go up the tree. And then you hash those 2 transactions together, and that's when you get this CD. And then you hash the hashes of the hashes together, and then you end up with your Merkle root. And the reason that this is an important thing is because if I'm trying to say, hey, was this transaction that I have, was it in a certain block? Is there proof that this transaction exists in a certain block? All you need, you need the hash of the transaction you're looking for, and you need the block header of the block that it was in, and then you can look up the Merkle tree and say, hey, I have my transaction here. I can hash it against, and you receive something called a Merkle path, which is just this blue, all of these blue things, all of these blue hashes. So I say, okay, the first one, if I hash those together, I get this, and I'll take the next thing in the Merkle path, perfect here. I say, okay, I'll hash my result here with that, and then I get the next thing in the Merkle path, hash those together, get the next thing in the Merkle path, hash those together, and then I can see if this equals the Merkle root that I had previously. So this means that I don't need all of these transactions, which it's more like 1,000 and not like 15 or however many this is. If I just need maybe, I don't know, 20 instead of thousands. So it's very, very quick. It's it's better with resources, and you still get an accurate validation. So bits is another thing. Bits it's more the target. It's not the difficulty, but you use the bits to find the difficulty. And it's the number to beat when you're doing your cryptographic hashing problem. So this is the bits. This is probably really hard to see, sorry, especially with the wonderful colors that I picked. If you have the bits which are inside of the block header, so if I look, this is an actual block from a few weeks ago that was mined on Bitcoin's blockchain. It has this bits number. Bits it uses like a kind of like a scientific notation. So you separate the 17 from the 43 ECA9. And the 17 is kind of if you have like 5.2 times 10 to the 20th. The 10 to the 20th means you move 20 decimal places. It's the same, but with bytes. So you move 17 is hex. So what is that? 16 plus 7 is 23 bytes. So you would take this number, subtract the amount of bytes it is, which is 3, from this 23, which I just said, and then you add that many zeros extra to the end of this hash, or of this hex number, and then you get yourself a hex number, which in this case is like 0x43ECA9 with how many zeros? A lot of zeros after it. And then you take that and you can turn it into an integer if that's easier to read, which it is, even though it's not, because this is a huge number. And this is the number that you're trying to get under with your cryptographic puzzle. So the nonce is it's a number that's only used once. This is what the miners are trying to guess. So so you have all of these numbers, you have all of these things in your block header. You have the version number, the previous block hash, the Merkle root, the time, the bits, and the nonce. And what you're trying to do is find a nonce that when you hash all of these numbers together, using SHA-256 2 times, you end up with a number that is less than what your target is. Or in this case, this 65, 6 whatever, quintiquad decatrillion, or whatever this number is. So I want to guess a number that when combined with these other numbers and hashed is less than this number that is our difficulty. And you can see what people often use as an example is how many leading zeros it has. I don't know if this is a good example of that, but for example, you want to find a number that has say if you were trying to hash this and then find a number that only has 1 leading zero, you would have, if it was binary, you would have a 1 in 2 chance of guessing that number. And if you moved it to being 2 zeros, then it would be a 1 in 4 chance, and then 3 zeros would be a 1 in 8 chance, going on further and further. So in this case, it's with Bitcoin now, I think it's like, I don't know, it's a lot of leading zeros, and it's much, much harder to guess a number that's lower than that. So here's our nonce. We take the SHA-256 of the header. We then take a SHA-256 again of that, because we're double hashing things. And then you can see that this number has however many leading zeros this is, maybe 9. So that's kind of what we're trying to go for here. Then once you solve that, you send this block to all of the nodes you know, and they verify that your hash is under the difficulty of all of the nodes. So you eventually get your block and you win. So we're going to try and make this Ruby related, and we're going to build our own mini stupid blockchain. I don't want to add a lot of things because then we would think more about the implementation than what we're actually trying to figure out. So our blockchain is, you can set a difficulty on it. So you can set this number where the leading zeros and all these things. Then a block just is very, very simple. It has a height, a difficulty, the previous block hash, a nonce, and a timestamp. And then the miner just is guessing these things. So we're not even doing transactions, so you actually can't do anything with our blockchain, just to keep it as simple as possible. Because then we'd have to think about kind of what transactions look like in a list, what are transactions. Woo, that's great. So maybe I just describe this. So we're creating a blockchain. There's a blockchain class that takes in either the initial target. So we're saying how many leading zeros we want. So if I want 20 leading zeros, I would put 20, and then the target would have to be less than whatever the hex number with 20 leading zeros is. Or we set it just to be 2 leading zeros because that doesn't take very much time. What's happening next? So you can add a block to the blockchain. It's just an array of block classes, block objects. And you can validate whether a block is valid or not, but that validation is taken care of on the block, which is maybe more legible. And with a block, you give it a target, and you give it the previous block. It knows about where it is in the blockchain. You can get the hash of it by doing a double hash. And you can check if it's valid to see if the hash of this block is less than the target. And the header you can see at the bottom is a combination of the previous block's hash, the target, and the timestamp. So with a miner, you take the blockchain, and then to mine a block, what I'm going to do is, normally the numbers are chosen at random, but we're just going to start with 0 and work our way up to whatever number we make it to that satisfies our difficulty. So we get the template, then we set the nonce, and then we check if it's valid. So if the header combined together with a nonce is valid, then we're good to go. If we're good to go, we move on to add the block to the blockchain, and then we return the block. So that's our miner. This is double hash. It just runs the 256 hash twice, like you saw in that other example. So I'm going to try and do a demo right now, which pretty much almost never goes well for me. And is there... So, are we there? Good. So far, so good. Okay, so we're going to run pry, which if you're not using that, if you're using IRB, I highly suggest you use pry. It's wonderful. Has lots of nice built-in tools like LS blockchain, for example, which gives us all of the methods for a blockchain instance, where I think the way that I used to do this was to be like, what is it? Whatever thing I'm looking for, .methods minus object.methods .sort, which is not beautiful. Like, pry is wonderful. So if you get anything out of this talk. So we're going to create a blockchain. The first thing that it does is it prints out the difficulty here. So the target. So the number that the miner has to solve, the number that they have to hash together and be less than, is 00 F, a bunch of Fs, which is a very, very large number, which you can see below on the target. That's that number in integer. So it's big. And then we can create a miner. The miner takes a blockchain. So we have a miner now. So now we can start to actually mine blocks. So our first block took 198 iterations after the nonces to find a hash that was lower than our target. So we can run it again. And you can also see that we were looking for a number with 2 leading zeros. You can see maybe I can make this even bigger. You can see here that the hash of our block has 2 leading zeros in it. So that's, I guess that's interesting. So what's happening now? We go another one. This one took 838, 243. So this is boring. Let's create a blockchain with a higher difficulty. So let's go with 4 leading zeros. Create a new miner with that chain, and then try and mine a block. And you can see that we got up to 103,107. That's how many times it had to guess. We run another one, and you can see that it's taking longer also for the thing to run. So this is where you start taking chances with the demo. Let's go, we're just going to go to 5. I'm not going to be crazy. So create our new miner. So the way that Bitcoin ensures that when there's thousands and thousands of new miners coming on and the hash power goes up incredibly, that blocks aren't being mined too quickly, is that every 2 weeks or every 2016 blocks, since the block time is 10 minutes, 2016 times 10 minutes is 2 weeks. You wait for 2016 blocks to happen, and then all of the nodes say, okay, was 2016 blocks ago, did that happen in 2 weeks? Did it happen in more than 2 weeks? Or did it happen in less than 2 weeks? And if it happened in less than 2 weeks, say it happened in 1 week, you can tell that, oh, the hash power has gone up incredibly since the last time I checked, so I need to make the difficulty much higher. So that should balance out to being the next time it comes being 2 weeks. But in the case of one coin that I've been mining recently, all of a sudden we got a ton of hashing power from China, and like blocks were going by crazy. They recalculate every 2,000 blocks, and after 2,000 blocks went by, they recalculated and the difficulty went through the roof, and it became kind of not very profitable to mine anymore. So all of the Chinese miners took off. They're like, screw you guys, we're out of here. They took off, and so the hash power went way back down. So what the deal is now is that there's an incredible amount of difficulty and no hash power until 2,000 blocks have gone by. But blocks right now are taking like multiple hours instead of 10 minutes like they're supposed to take. So by the time the 2,000 blocks happen again, it will be in months instead of a couple of days or a few days. So everyone is pretty, like, this coin is fairly dead right now because of this situation. So you can change the nodes all change the difficulty based on what has happened over the last 2000. I hope 2016 is correct. If anyone has a calculator to do the multiplication with that one. And that's what's happening. You can see that if I'm the only one mining and you want to keep this, that each, for example, this is taking how long now? So maybe like 13 seconds. If I need that to actually take 2 minutes, Say my block time is 1 minute. I would need to make this difficulty like 7 more times, so 8 more times difficult than it is right now for me to, on average, mine a block every 1 minute. So that's what this difficulty is. It's constantly being retargeted. Proof of work, yay, good times. So I have no idea where I am for time. I was going to set a timer, but I didn't. Is there anyone tracking? You know how much time I have? Okay, what time is it? 40 after? When should I be done? Whatever. So there are some alternatives that are less energy crazy. Here are some of them. Proof of stake, which Ethereum, which is the second most popular cryptocurrency, they are planning to switch to proof of stake very soon. There's proof of burn, proof of identity or authority, proof of time, many other things. So with proof of stake, you have, instead of this proof of work algorithm that's proving that you're working on stuff, you take coins that you own, so say 50 Ethereum, and you stake those in a wallet. You send those to some sort of a wallet where it stays. So I go through, and there's an idea of an epoch. And an epoch, am I pronouncing that right? I have no idea. Epoch, there we go. There's an epoch. I only think of Tupac now when I say. So there's an epoch that is split into multiple kind of time pieces, and really good. And each time one of these amounts of time goes by, someone gets to validate a block. If I have more money in the system, if I have more Ethereum in the system, the chance of me mining a block, it goes up. Or me being chosen to mine a block goes up. So every certain time period, these things go by, great, these blocks are being mined. So with proof of work, the thing that you're risking as a miner is energy. So I'm spending a lot of money on energy, and if I do something bad and it doesn't go my way, then I just wasted a bunch of energy and money to do that. The way that proof of stake works is if you're a bad actor, they pretty much take your stake, your 50 Ethereum or whatever you have staked, and they burn it. It like doesn't exist anymore. So it's actual currency that is being burned instead of real world resources. So there is some positive, negative things about it. It's really hard to find out kind of what makes sense or not, because the arguments for both sides are both good. So yeah, they burn it. I forgot about my animation. So proof of burn. In this, you take your coins and you send them to a burn address, which either locks them forever or just burns them, like they don't exist anymore. Or you can sometimes there's like things that pick random addresses that you send money to, which is very unlikely to be a real address. And what happens is by how much coins you've burned, which can be seen in the blockchain, you have a history of how much people have sent to these addresses. If you send more coins, you have more of a chance to validate blocks in the future. And yeah, so that's how that works. You get chosen like you do with proof of stake, but you're burning these things and then receiving hopefully more money in the end. And this is a good system in the way that if you have it burnt, if you've burnt your coins in this system, then you have more of an incentive to stay within this system and not take your stake and jump to another coin. Proof of identity is another one where the validators are chosen beforehand, and they're like notaries or people that have a public identity that is verifiable. And in this case, if you do something bad, your reputation is on the line, and your real address is known. So if you're doing really, really shady stuff, it can be tracked back to you. And this guy said this, yeah, reputations are important. they're easy to destroy. Proof of capacity is another one that's interesting that you use storage. So you kind of pre-hash your hard drives with different solutions somehow. Like obviously I don't really understand this one very well. And then, so you, in this case, instead of having a bunch of GPUs next to each other, you would have like a whole stack of lots and lots of hard drives. And this significantly is another one. All of these do something where you're not using tons and tons and tons and tons of energy. It's really just like, instead you're buying old hard drives or something. And then it's very light to actually validate stuff. And that's all I got. I really have no idea if I went over. Thank you. And if there's a couple of questions, like, yeah, I'm gonna or talk to me about it afterward too. That's completely a thing that's possible too.